Okay, welcome back. And we're going to be looking today at the microscopic processes for elastic behavior, which is the modulus. This is the measure that we use for elasticity. And we're also going to look at processes for plastic deformation. And we're going to discover that as we look at some real data that engineering stress and strain have some problems. And so we're going to look at a solution to that problem, true stress, true strain, and give you the tools to convert between them. And obviously I gave you modulus values last discussion, and you should be, at this point, should know those values. Now, elastic deformation is very simple. It is simply the stretching of the bonds between atoms or molecules. And the energy well in which those atoms reside when they're in bonds, when they're bonded to each other, are such that if you compress them together or pull them apart, you have pretty much the same resistance. And the aggregate effect of all of these individual bonds being stretched is that you measure a modulus. And the modulus should be the same in tension as it is in compression. Now, plastic deformation is a little different animal. And to start thinking about it, let's do a thought experiment. This is a classic experiment in materials. And we're going to take a magnesium single crystal. So they're going to grow the metal in, so it's a single crystal, no grain boundaries. And then what we want to do is we're going to cut a tensile specimen out of that single crystal. And if you remember, magnesium is hexagonal close packed. And the close packed plane aligns with the base or the top, either one of a hexagonal cell. And so what we want to do is orient that basal plane at an angle of 45 degrees with respect to the load direction. And we're basically stacking the experiment to produce a desired result. Now, if we then pull on that bar in a tension test, we're going to see tremendous amounts of slippage. And so the bar is going to deform, and it's going to develop these slip bands. And the slip bands, if we zoom in on them, consist of many slip tracks or lines. And basically, it looks like the material has slipped past, parallel planes of material have slipped past each other, and that's how this deformation has occurred. It's very dramatic, and needs to be explained, obviously. We need a mechanism for this. So we get a stress-strain curve for the magnesium in this test, the simple crystal, and we get a yield strength of about 0.7 MPa. So we'll come back to this and use these values in a moment. Now, thinking about what's happening, the simplest explanation is that we oriented close-packed basal planes at 45 degrees. Well, that's the planes on which the slippage appears to be occurring. So what we must have, well, at least what it appears we have, is close-packed planes of atoms sliding past each other. And so atoms are nested. They're pushed up to the saddle position, and then they drop down into the next spot, and that produces a slip step. All right, well, reasonable mechanism. I don't think any laws of physics are violated. So let's look at what that's going to require. So let's push an atom from its equilibrium position up to the saddle point. So it's shifted to the left a distance equal to the radius, approximately, of the atom. And the height, if we think in terms of this one, it's kind of hard to measure height when it's in its starting position, is approximately 2a. So we have a horizontal shift divided by original height is my shear strain. Go back to the definition, shift divided by height. And so I have a shear strain of approximately 1/2. That's very much approximately 1/2. Now, let's go use Hooke's law. Okay, here's Hooke's law for shear. Shear stress, shear strain, shear modulus. For magnesium, shear modulus is about 17.2 gigapascals. So I put a half in here for the strain, multiplied by 17.2. The shear stress that should have caused this is about 8.6 thousand megapascals, or 8.6 gigapascals. Now, what was the yield strength that we saw on the stress-strain curve? Was 0.7 megapascals. So rather than 0.7 megapascals, we have 8,600 megapascals. Sorry, there's an error here. This should be MPa, not PA. And so we're going to error about 10,000 times. Now, obviously something's wrong, right, with our model. And here's the key. We do not, in fact, get slippage of close packed planes past each other. This is not the process that's occurring. What's occurring is dislocations that we've already defined are going to move. And it's the movement of dislocations that allows us to produce slip steps. So it looks something like this. Start with a crystal, we apply a shear stress, pop into that shear stress a dislocation. Continue to apply the shear stress, the dislocation pops through one bond at a time. Bingo. Slip step, but we've only broken one bond at a time. We've not broken all of them simultaneously. So this is the actual mechanism of plastic deformation. It's dislocation, movement through a crystal. So we're breaking individual bonds, not all the bonds at one time. Now, a good analogy for this is if you've ever laid carpet, you know when you unroll the carpet, it's never aligned perfectly. It's too far to one side or the other. And so you can't get down and slide the carpet. What you do is if it's too far this direction, you pick up the edge and line it up where you want it, and you put a hump in the carpet. You then push that hump through, and as that hump pushes through, you're literally picking up excess carpet, packing it up vertically into space, and then sliding it along and laying it down at the other end. Now, this is a dislocation. What is a dislocation? It's an extra half plane of material packed in where there's no room. So, in this case, you're overcoming friction, not all the bonds at once, but by breaking the bonds locally and then laying things back down again. Okay? Now, slip only happens on slip systems. That is, you really aren't going to get slip on all planes, only on close packed planes, and only in directions where the atoms are close packed. So you'll get slip here, you'll get slip here, but you will not get slip vertically because the atoms are not all close packed together. So there's limited directions and limited planes. And this is the reason for the difference in the behavior of FCC, BCC, and HCP metals. FCC materials have many degrees of freedom, many slip systems available, and which allows dislocations to move through the crystals to maintain contact with each other while changing shape, because there's plenty of slip systems and plenty of degrees of freedom. The problem with FCC materials is even though they have a good number of slip systems, they're interconnected in ways that limit the freedom of the crystals to deform. And so they don't deform as easily. Now, so summarizing, elastic deformation is due to bond stretching, and because we're just stretching bonds, volume is not constant. Poisson's ratio is not usually 0.5. Plastic deformation, however, is due to slipping of dislocations, and so the volume will be constant. Now, I use mu here because if you're looking at a manufacturing book, for some reason they like to use mu rather than nu for Poisson's ratio. But mu or nu, whatever it is, Poisson's ratio for plastic deformation is 0.5 because if you shuffle dislocations around, you haven't changed any of the bond lengths. And so the total volume of the material doesn't change in plastic deformation. Now, let's think about the properties and what do we expect when we go from tension to compression. Modulus is simply bond stretching. It's the same in tension and compression. Yield behavior is caused by shear stresses. Now, if the shear stresses are generated by compression, they're going to be pushing one way. But if they're generated by tensile stresses, they're going to be pushing another direction, opposite direction. But they're going to be sliding or acting in the same plane. And so essentially, yield behavior should not depend on whether we're talking compression and tension. And if the mechanisms do not depend on compression or tension, then we should see the same behavior in a stress-strain curve in compression and tension. And in fact, we do not. So here we're looking at force over area. This is stress, engineering stress, change in length over original length. So we're plotting tension, tension. That would be a tension test. And this would be negative, negative, or a compression test. And these curves should be mirror images. They are not, which means either something's wrong with our mechanisms or something's wrong with our test. And the problem lies with how we define stress and strain in this situation. If you think about the problem, in a compression test, as you compress the material, you started out with some area A0, but as you continue to load it, the area is increasing. So out here where I'm calculating a particular stress value using the original cross-section, that's not actually the cross-section that exists there. Similarly, in tension, the sample is shrinking. We're getting reduction. And so we're going to be off because of that. So here's your problem. In compression, the area is increasing. In tension, the area is decreasing. So the actual stress isn't going to be accurate if we're dividing by original area. We have to divide by the instantaneous area of those two in the two situations. Okay? Now, what happens, or how do we fix that? Well, we simply measure the area continuously or instantaneously. And from that, we can calculate what we call a true stress curve. So force over instantaneous area is sigma, and I'll try to use sigma for true stress, S for engineering to avoid confusing you. So here's our tension curve. Here's the compression curve that we get. If they were perfectly symmetric, then this dashed line is what we would get for the compression curve. So we still haven't solved the problem completely. It's better, obviously, they have the same general shape, but there's still a little bit of an error. And that error obviously falls in their definition of strain. We fix stress, that fixes most of the trouble. If we fix the strain definition, that's going to solve the rest of it. And so here's the problem with strain. Let's take a bar, L's length L. We'll take two bars. Both of them are length L0. We're going to stretch one of them 10%. So its new length is 1.1 L0. We're going to compress the other one 10%. So its new length is 0.9 L0. Okay? So we're going to take those two bars that are already compressed or stretched. We're going to apply another 10% strain, according to our engineering definition. So I'm going to apply another 0.1 L0 extension. But this is being divided by the length before we applied it, which is 1.1. So I'm going to have 0.1 divided by 1.1, or about 9% strain is the amount of strain I'm generating there. On the shorter bar that has already been shortened, when I apply that same deformation, I'm dividing by a smaller original length. And so I end up with about 11% strain. So the strain is becoming more intense in compression and less intense in tension because I have a longer bar. Now, how do we fix it? Well, we got to go calculus. If my change in length is infinitesimally small, then strain will be perfectly the same in tension and compression. Change in length over length, perfectly the same in tension and compression if dl is approaching 0 in magnitude. Now, you can't really approach 0. This is a calculus concept, right? The concept of the limit. So what we get is an increment of strain is going to be an increment of change in length, okay, divided by the original length. If I want to know the strain at a point, I have to integrate this. And if you haven't had calculus, that's okay, doesn't matter. But we'll integrate from L0 to L by current length, and we'll integrate this from L0 to L. And so you end up with strain is the integral of 1 over L dl is going to give you natural log, right? You apply the limits of integration. And so the true strain is the log of the instantaneous length divided by the original length. And if you do that, now the tensile and the compressive curves are exactly mirror images of each other, which they should be. All right? Now, how do we convert? Or why do we care? Well, if you start with your engineering stress strain curve here, you have your maximum load, your ultimate tensile strength that you can calculate, strain to failure, all that good stuff, right? If we correct and calculate the true stress, true strain behavior in the neck of the material, we'll get this other line. Now, if you look down here, if I want modulus, does it matter which curve I use? No, it doesn't. If I want offset yield strength, does it matter? No, probably doesn't matter there either. If I want ultimate tensile strength, I can't identify the ultimate tensile strength here. All I can give you is the stress in the neck at fracture. So I want the engineering curve for ultimate tensile strength. That's actually very, very helpful. And so the main reason we'll use true stress, true strain is you'll have opportunity, depending on which industry you end up in, to do design work with parts that are intended to deform permanently before they go into service. So it's called post-yield design. You may need to do this if you're talking about manufacturing processes where you're drawing or stamping metals or other materials beyond their yield point, in order to shape them. And so in that case, you need to know the true stress and true strain behavior of the material, and that's where you'll have cause to use these conversions and this kind of a stress-strain curve. So how do you convert between them? These are the two simple equations. You will have these equations in your equation book. You're not expected to memorize them. You just need to remember E is engineering strain, change in length of original length. Stress is S is engineering stress, force divided by original area, and then these are the true values, sigma and epsilon. And you can convert from engineering to true or from true back to engineering. Okay? Now, stress-strain curves have other value to us besides giving us all those parameters we've talked about. The area under a stress-strain curve is the work that has been done on the sample in stretching all of the bonds and in moving all the dislocations. And if this is a stress-strain curve, the area actually will have units of energy per unit volume. So it's a specific energy. And if you have an elastic material where you loaded it up, this would be rubber elasticity, and then you unloaded it. How much energy went in when you loaded it up? It's the area under the curve. How much energy came back when you unloaded it? The area under the curve. It returned that energy to the outside world. And we have that area under the curve is an indicator of brittle versus ductile behavior. So a brittle material, area under the curve is small. That means the energy per unit volume required to fracture it is not very great. Ductile materials, this energy, the area is large, which means very high energy per unit volume to fracture. Ductile, probably tough material. Brittle, okay, not a tough material. Now, one other thing that the stress-strain curve can give us is some materials will dissipate energy internally. So think of this as a two-step process. We're going to load it up. The area under the load-up curve is the work we just did on the specimen. When you unload, if we go back to a stress-strain curve, let's go back to a linear one here. When I unload, the specimen is pulling on the frame as we unload, and so the force the specimen applies in the direction of the specimen movement is doing the same work, but now it's doing it on the outside world and returning the strain energy to the outside, to the frame or whatever we're loading with. So the area on the load up is the area put into the specimen. The area on the unload is the area the specimen puts back. If I have perfectly elastic behavior, they're the same area. However, in some materials, the load up curve is not the same as the unload curve. And so the area under the load up curve is the work we put in. The area under the unload curve is the work the sample gives back. And the difference between them is the energy we put in that didn't come back. So your spring isn't springy, the ball doesn't bounce, because the energy of compression is dissipated internally, and it's dissipated as heat. And so materials warm up. And we can use this. We have some really high loss materials where the unload curve may do something like this, and you may have 80 or 90% of the energy that went in disappears. And so you build rubber balls that don't bounce, shoes that are not too bouncy, that absorb shock, so on. And so this is called hysteresis, or anelasticity, that is not elastic, okay, the absence of elastic behavior, and we get energy dissipation in the material. All right, totally changing gears, just a little reminder. Hardness is very closely related to the strengths that we've been talking about. And hardness is simply resistance, as you found in lab, to permanent deformation of the surface. Large hardness means that the material is very resistant to plastic deformation. And high hardness usually is going to improve our wear behavior, we'll be talking about here in a couple weeks. So the classic test is the Brittle test, which takes a 10-millimeter sphere, you push it in. When you remove it, there's a spring back here. This hole is going to be larger in this case. All that's left is the permanent hole. You measure the size of that permanent hole, and you are then going to divide, essentially you're going to divide the force that you applied to the sphere by the area of that hole. And so Brittle hardness is actually given in units of stress. The Rockwell hardness that you all have done is just given as a number, doesn't have units of stress. But it's analogous. It's measuring exactly the same thing, resistance to permanent deformation. Now the key here is this quantity, the hardness, however you measure it, is very closely related to yield strength and ultimate tensile strength. And so we'll often use hardness as a substitute or a proxy when we want to measure yield strength and we can't make a tensile bar, we want to measure ultimate strength and we don't have anything we can break. We'll measure the hardness, and because they're closely related, we can estimate one from the other. And in fact, your conversion chart you've used in lab, if you're paying attention, when you converted from C scale to A scale, there's a far right-hand column which is tensile strength. And that is the approximate ultimate tensile strength of a material that has that hardness, at least a ferrous material that has that hardness. All right, that concludes this session. We'll talk to you next about mechanisms of strengthening and how we can adjust the strength of our materials.